For this video, I'm going to show you an animation that I created that demonstrates how a convolution kernel works on an image. This is in the context of computer vision, neural networks, that sort of thing. Don't worry too much about the parameters here if you don't know them. I'm just going to show you the animation first, and then I'll describe the parameters. Alright, so this is the animation. You can see that don't worry about the movement yet, but the blue pixels, that represents the image, and that will be 12 by 14 in this case, because that's what I've set the parameters as. This is the kernel, these black X's being moved along the screen. That is 2 by 2, and that is equivalent to a kernel size of 2. So if this was 3, then this would be 3 by 3. The stride is the movement of the kernel, so a stride of 1 means it moves one step to the right. And then after the row has finished, it moves one step down. So it starts here, and then the next row that it takes would be over here, and the next one would be over here. The padding is the red pixels here, or the red points, and that represents a sort of extension to the image. And I'll explain that in a second. But images are represented by numbers in neural networks anyways. So you can think of these blue points each as a number representing a pixel of the image. And now this black X here, or these black X's, the kernel, that also is typically represented by numbers, and it performs a mathematical operation on all the pixels that it covers. That's the way that a convolution kernel works, and I'll describe more as we go. Now the padding, that is sort of an extension, like I said, to the image. Imagine that you had a kernel that was over here, and it was 2 by 2. Let's say this was the point where, or these were the points where it was at, and then it needed to take 2 steps because the stride was set to 2. If we didn't have this padding over here on this side, then it wouldn't be able to go any further on this side because there's only this one column here. So it would have to skip this column and just go to the next row. That isn't ideal because that means that these corner bits, these edge bits, aren't being represented in the mathematical calculation, in the mathematical operation. So this padding is set as a sort of way to extend it so that the kernel, if required, can calculate these edge parts as well. So padding is not necessarily required, but if it's needed, then it can be added. And usually the padding, well, a typical case is just to set it equal to 0, all those cases, all those pixels, but you know, there's different ways to do it depending on the problem. So you can perform an operation on the corner parts, or you can just extend the corner parts directly by just making them the exact same. But from what I've seen, just 0 is a typical value for all the padding. That way the edge parts can be incorporated. Alright, let's go to the next one. Alright, next one I'm going to show you is a stride of 2. It's a little bit laggy, but you can see that the stride is 2, so now it's moving 2 spaces to the right, and then when it gets there, it'll move 2 spaces down. So it moves 2 spaces, or it moves stride spaces to the right, and then stride spaces down. Now the kernel doesn't just hover over the pixels, like I said, it doesn't do nothing. It performs a mathematical operation on the pixels. For example, the kernel values might just be like numbers, and then you're multiplying them by the image pixels and then dividing by 4, which is the amount of X's in the kernel, so the amount of points in the kernel. That could be a typical calculation, and then that would produce a result, a scalar, one number, and that would be a new pixel, which would be in the resultant image. So that's the way it performs calculation. So it would start here, for example, and then it would perform that calculation, resulting in one number, and that number would be transferred to the resultant image, and that would be a pixel in the image. And then it would go to the next one, perform the operation, and that's a new pixel in the resultant image. So you can imagine that if the stride, like, think of it this way, if the stride was something like 6, an extreme example, then it would skip a lot of pixels, and therefore the resultant image would be smaller. Now that's typically the case where the resultant image is smaller than the starting image, but it's not just about making it smaller, making the height and the width, the dimensions less, that's what I mean by smaller. But it's also about smoothing out the image and making the important parts stay while the not important parts disappear. And the way it does that is, well, you can see that the kernel is on a group of pixels. So you can imagine that we could add a certain combination of numbers that would make it smooth it out. And there's also a certain combination of numbers that only highlight the edges of the specific picture. And that could be useful because imagine passing in an entire image, just a typical image where it has a lot of information, a lot of different important parts in it, into a neural network, a typical neural network. That could overcomplicate things, and the neural network might feel overwhelmed by all the information. That's why it's useful to kind of only highlight the important parts. That could potentially make the network perform better and also faster as well. We're going to look at a larger image now because it's not typical that you'll see 12 by 14 pixels. 4, 2, and 1. There we go. Oh, not 82, 28. Now, I'm pretty sure this is the MNIST dimensions, you know, the handwritten digits from 0 to 9. I'm pretty sure they're 28 by 28. Sometimes you can get, you know, heights and width up to like 500 or 1000 in some cases, in which case it might be useful to actually reduce the size before you put into the convolution. Yeah. Alright, so kernel size 4, stride 2, padding 1. So this looks a lot nicer actually as well. You can see that it's 30 by 30, and the reason for that is because the blue represents the 28 by 28, but then the added padding contributes to an extra 2 points in each dimension. So that's why you get 30 by 30. Don't worry too much about the axes. That's just for my benefit when I was coding the program, but they're not that important for this video's purposes. Yeah, so you can see that the kernel was 4 by 4 in this case. So if you were taking a sort of weighted average calculation, then you would first multiply all the numbers by the image, all the numbers of the kernel by the pixel that they're on, and then divide by 16 in this case because you got 4 by 4 kernel. And the stride is 2, so you can see it taking 2 spots, 2 spaces like that. Padding is 1, you can see that there's the outer section here. I'll just show you a padding of 2 just to demonstrate that it can be more than 1. There you go. So now the padding is thicker. And again, it's a little bit laggy, but you can see the idea. Let's just wait for it to get to the row so you can see what happens. There you go. I'm just going to give you another example just for my curiosity and maybe yours as well. I'm going to set the stride to something huge, 14. And you can see that what will happen here is that it will take 14 spaces with every step. Now this probably won't be useful in a actual situation. And you can see that there'd only be, what, 1, 2, 3, 4, 5, 6, 7, 8, 9. There'd only be 9 pixels in the resultant image because there's only 9 iterations, or whatever you want to call it, 9 movements of the kernel. So anyways, that is how convolution looks like in a computer vision problem. Thanks for watching. I hope that helped.